Hi, this is David. Today we're going to talk about points to analysis, and this is just going to be a brief overview. So to start off, what do we mean by points to analysis? Well, imagine that we've declared an integer array A with 10 members. The variable A points to some memory location containing, 10 different memory cells of size int. And so points to analysis is an analysis concerned with understanding these points to relationships. A closely related concept is that of alias analysis. Now, alias analysis is a Boolean function that returns true when two pointers P and Q may or must point to the same area of memory. A lot of points to analysis will compute an alias analysis Boolean function. So let's look at an example. In this example, we have an integer x, and then we have a pointer P equaling %x. So the ampersand here means that we take the address of x. Then we assign another pointer q to be equal to p. Now at this point, q and p are aliased. So if we have an alias analysis, we would expect is aliased p and q to return true. We then take the address of some different variable y and assign that to r, and if we call is aliased on p and r, we'd expect that to return false. There are at least 6 different dimensions to designing a points to analysis. First, whether the analysis will be inter or intra-procedural. Intra-procedural means looking at only a single procedure, and inter-procedural means looking at alias relationships and points to relationships between procedure calls. Second, whether the analysis will be flow-sensitive or flow-insensitive. Flow-sensitive means that we look at the order of statements and take that into consideration, while flow-insensitive means we compute one solution. Third, whether the analysis is context-sensitive or context-insensitive. Context here refers to a calling context. So what this means is whether we take the calling context into consideration when thinking about alias and points to relationships. Fourth, whether or not the analysis is a may versus a must. In other words, whether it's going to return whether two pointers may point to the same thing or whether they must point to the same thing. Fifth, how structure fields, objects, and etc. are handled. And sixth, the representation and data structures used in the analysis itself. Now, at a high level, typically we're looking for an inter-procedural analysis, and that's because, we want to look at alias relationships between procedures. Second, flow-sensitive analysis, although desirable, is usually too expensive unless great care is taken. Now, one can use a flow-insensitive analysis, but prior to computing a flow-insensitive solution, convert the program into SSA form as a type of poor man's flow-sensitive analysis. Third, context-sensitive analysis tends to be more practical in the research. Fourth, really you're going to want both a may and a must analysis. For example, in liveness analysis, you're going to probably be using a may and a must to decide gen and kill set. So computing both makes a lot of sense. For 5 and 6, there's lots of research. For example, when we look at representation and data structures, we see a lot of research focusing on using BDDs, for example. Now, there's 2 basic general approaches to doing points to analysis. First, there's Anderson-style analysis. Now, the Anderson-style analysis comes from a PhD thesis from 1994. At a high level, it uses what's called subsets constraints and has a time complexity of O(n) cubed, where n is the number of statements in the program. Second, there's Steensgaard style, which is a paper that comes out of Microsoft in 1995. Now, Steensgaard was trying to address some of the complexity in the Anderson style analysis, and instead of using subset constraints, he uses equality constraints. And this leads to a linear runtime. In general, Anderson style points to analysis will be less scalable, but more precise, while Steensgaard style will be more scalable and less precise. All right, that's the end of the overview.